Module 3, Lecture A, Algebra for Models. By the end of this lecture, you will be able to interpret simple linear equations used to express model predictions, differentiate between variables representing inputs and parameters representing model choices, and predict qualitatively how changing a parameter affects the output of a simple model. Linear model expressions. Reading input variables. When working with a simple linear model, it is important to understand what the input variable represents in the real world. This variable stands for a measurable quantity, such as study hours or temperature, and is not just a letter, but a placeholder for actual observed data. You should know what it stands for, what units it uses, and what range of values makes sense. For example, if it represents machine hours in a day, it cannot be negative or greater than 24. Connecting the abstract symbol to a concrete quantity is essential for making sense of the model's predictions. After you understand what the input variable represents, the next step is to connect it to the model's output, which is what the model predicts or explains. You should be able to describe in simple language how changes in the input affect the output, such as whether increasing the input tends to increase or decrease the result. Even without exact numbers, you can judge if larger inputs lead to larger or smaller outputs, and whether that pattern seems reasonable based on your own knowledge. Translating the model's symbols into everyday language in this way helps ensure the model's behavior matches your intuition. The same symbol in a model can represent very different things depending on the context, such as age in health studies, commute distance in transportation, or advertising spend in marketing. Even if two models look similar on paper, the meaning of their inputs and how you interpret their predictions can change completely with the setting. You should always restate what the input actually measures, where it applies, and any natural limits it has. This helps you focus on the real-world meaning of the model, not just on manipulating abstract symbols. Understanding slope and intercept. In a simple linear model, the slope and intercept describe how inputs relate to outputs. The intercept is the predicted output when the input is 0, like a starting fee. The slope shows how much the output changes as the input increases, such as the cost added per kilometer. A larger slope means the output rises more quickly, while a smaller slope means a slower increase. Together, they summarize the model's assumptions about the baseline level and the rate of change. Slope describes how much the output of a model changes when the input increases by 1 unit. In a model predicting exam scores from study hours, the slope tells you how many extra points are expected for each additional hour studied. A positive slope means more of the input leads to more of the output, while a negative slope means more input leads to less output, such as more phone use leading to shorter battery life. The larger the slope, the more sensitive the prediction is to changes in the input, and understanding this helps connect model numbers to real-world behavior. In a linear model, the intercept needs careful interpretation because it does not always have a clear real-world meaning. Sometimes it represents a real baseline you can observe, like the starting fee in a taxi fare. Other times, such as predicting blood pressure from age when your data only includes adults, the intercept at age 0 does not correspond to any realistic case and is mainly a mathematical requirement. Overall, the intercept sets the vertical position of the prediction line, while the slope controls its tilt, and both must be interpreted in the context of the problem. Multiple input terms. When a model uses multiple inputs, its prediction depends on several factors at the same time, rather than a single cause and effect. For example, a model predicting a student's final score might use homework, exams, and participation, with each input representing a different aspect of performance. The model combines these inputs with a baseline level to produce the final prediction. This means no single input fully determines the outcome. Instead, Each one contributes its own weight to the result. To understand models with multiple inputs, look at how each factor affects the outcome while holding the others constant. For example, in a course score model, you can fix exam and participation levels and see how changing homework scores alters the prediction. In a housing model, different terms might capture the effects of square footage, number of bedrooms, or distance from the city. Each term isolates one influence, and the full model combines all these influences into a single predicted result. In models with multiple inputs, each input contributes to the prediction in an additive way, meaning changing one input does not change how the others affect the outcome. For instance, in a nutrition model, the effect of body weight on energy needs is treated separately from height or activity level. This creates a simplified view of reality, but it makes the model easier to interpret. You can think of it as starting from a baseline and then adding the effect of each factor in turn to reach the final prediction, which is the core idea behind linear models. Tuning model parameters. Inputs versus parameters. In a simple predictive model, it is important to distinguish between inputs and parameters. Inputs are external values that can change from one situation to another, and the model uses them to produce outputs. Parameters are internal settings that determine how strongly the model responds to those inputs. Unlike inputs, parameters stay fixed unless we deliberately change them. Consider a model that predicts household electricity use from the number of residents. The number of residents changes from one household to another and serves as the input, while the model includes a fixed parameter that represents average electricity use per person. You might adjust this parameter when analyzing a different location, but within a single analysis, it stays constant as the inputs vary. This setup, where inputs change and parameters remain stable, is widely used in areas such as economics and environmental science. In a model, it is important to distinguish between inputs and parameters. Inputs come from outside the model, such as environmental conditions or human actions, and you simply observe and feed them into the system. Parameters, on the other hand, are chosen by the model builder to control how the model responds. For example, how strongly sales forecasts react to advertising. When predictions are inaccurate, you typically adjust the parameters rather than the inputs. Understanding this difference helps you tune the model to improve its performance. Shaping model outputs. When we shape a model's outputs, we are really deciding how its parameters define overall behavior, while the inputs only move within that fixed structure. You can think of parameters as the dials on a machine, and inputs as the material going through it. The material can change, but the way it is transformed depends on how the dials are set. For example, when predicting a monthly electricity bill from home size, each home's square footage is an input. But changing the model's parameters changes the relationship between size and cost for all homes at once, without altering any individual input values. In a ride-sharing app, each trip price depends on changing inputs, like distance and time of day. But the overall pricing structure is controlled by parameters, such as the base fare, cost per kilometer, and a surge multiplier. If the company wants to raise rush hour prices, it can increase the surge multiplier, which raises all fares during that period without changing the individual ride inputs. This shows that parameters act as levers that adjust how sensitive the model is to its inputs and shape the overall pricing pattern. In many systems, it is important to distinguish between inputs and parameters. In a course, exam scores are inputs, while the instructor's weighting scheme is a set of parameters that define how all scores are combined. Changing one student's score only affects that student, but changing the weights alters the grading model for everyone. In a streaming service, your viewing history is input, and the emphasis placed on factors like similarity or popularity are parameters. Adjusting these parameters changes how recommendations are generated, so the model's outputs better match user goals. Python code shaping model outputs. This script demonstrates how changing model parameters affects the outputs. It uses a simple linear billing model as the example. The main goal is to explore how adjusting the parameters alters the results, rather than changing the input data itself. We begin by importing the pyplot module from matplotlib, a common Python tool for creating visualizations. In this script, we use it to build a plot that compares different parameter settings in a billing model. Pyplot provides functions for creating and customizing plots, including line and scatter plots. Using these tools, we can clearly show how changing parameters alters the model's outputs. This part of the code defines a bill model function that calculates a monthly bill using a simple linear formula. It takes the home size in square meters, a slope rate, and an intercept base as inputs. The function multiplies the slope rate by the home size and then adds the intercept base to get the bill. In this model, the slope rate is the cost per square meter, and the intercept base is a fixed cost that does not depend on home size. We begin by defining a list of home sizes in square meters, which will act as a common set of inputs for our billing model. Using the same home sizes each time lets us see how different parameter choices change the model's output. This approach keeps the input data fixed, so we can focus on how adjusting the parameters alone affects the results. In this scenario, we model a cheaper energy option by setting two key parameters for the monthly bill. The slope is set to 0.8, meaning the bill increases at this rate for each additional square meter of home size. The intercept is set to 20, which represents the fixed base cost of the bill that applies regardless of home size. Together, these values define how the monthly bill is calculated in a more affordable energy context. We now define parameters for a scenario where energy is more expensive. The slope is set to 1.4, meaning the cost per square meter increases more steeply than in the cheaper case. The intercept is set to 35, which represents a higher base cost that applies regardless of home size. These values will be used to calculate monthly bills for different home sizes and to compare how changing these parameters affects the overall billing model. We use a linear model to estimate monthly energy bills for different home sizes under a cheaper energy option. For each home size, we multiply the size by the cheaper rate and then add the cheaper base cost. We do this for every home size in our list and store the results in a list called cheap bills. This list represents the predicted monthly costs when using the cheaper energy scenario. We now calculate energy bills for a more expensive scenario by using higher cost parameters in our billing model. For each home size in our list, we plug in these more costly slope and intercept values. This gives us a new set of predicted bills that reflect the higher prices. The results show how energy costs increase with home size when the overall pricing is more expensive. We focus on a single example home size from our list by choosing the third entry, which is 80 square meters. Using this specific size lets us clearly see how changing different parameter settings influences the billing model's output. By holding the home size constant, we can more easily compare and understand the effects of each parameter on the final billing results. To estimate the bill for a particular home size using the cheaper energy option, we run the billing model with that home size, the lower slope rate, and the lower base intercept. This calculation gives us a predicted cost under the cheaper pricing conditions. We then store this value as the example cheap bill, which represents what the model expects the customer to pay with the less expensive energy parameters. To find the example expensive bill, we call the bill model function using a specific home size from our list, along with the slope and intercept that represent the more costly energy case. This calculation gives us the predicted bill for that home size under expensive energy conditions. We can then compare this result with predictions from other parameter settings to see how changing the slope and intercept affects the final bill. We display a message indicating the home size used for comparison to make it clear that the parameters change the billing rules, not the input size itself. This helps separate the idea of the data being processed from the way it is billed. By doing this, we highlight how adjusting different parameter settings can change the model's output and cost, even when the input remains exactly the same. We display the bill calculated using the cheaper parameter settings and format the result to 2 decimal places so it is clear and easy to compare. This simple output highlights how changing parameter choices can alter the model's result, even when the input stays the same. It helps you see the impact of configuration decisions on the final cost. This line prints the bill calculated using the expensive parameter settings. It displays a message that includes the phrase "bill with expensive parameters equals," followed by the bill amount. The amount is rounded to 2 decimal places to keep the output concise and easy to read. This makes it simpler to compare how different parameter settings change the bill for the same home size. We begin by creating a plotting window using a figure from matplotlib, setting its size to 6 by 4 inches to control the overall dimensions. This step prepares the space where we will display our results. With the figure in place, we can clearly visualize and compare how different parameter choices affect the behavior of our billing model. We use matplotlib to plot a line that shows how home size relates to the calculated bill when cheaper energy parameters are applied. The horizontal axis represents different home sizes, and the vertical axis shows the corresponding bills. Circular markers emphasize each data point along this line, which is labeled as cheap parameters, to distinguish it from other scenarios. This plot helps us see how using cheaper parameter settings changes the billing model's output across various home sizes. We now plot the line that represents the expensive parameter settings by using home sizes as the horizontal values and the corresponding expensive bills as the vertical values. To make this line easy to distinguish from others, we display it with square markers. We also assign it the label expensive parameters so that it appears clearly identified in the legend. This helps the viewer quickly see which line corresponds to the expensive settings on the plot. The code uses a plotting library to label the x-axis as home size in square meters. This tells viewers that the horizontal axis represents the size of the home measured in square meters. Clear axis labels are important so people can quickly understand what the input variable is when they look at the plot. The code labels the y-axis of the plot as predicted monthly bill units. This tells the viewer that the vertical axis shows the model's predicted monthly bill amounts. Clear labeling makes it easier to understand what the plotted values represent. As a result, the plot becomes more informative and easier to interpret. The code sets a title for the plot that explains its purpose, to show how the same inputs can produce different outputs when only the model's parameters are changed. This highlights the impact of parameter variation on the model's predictions. It makes clear to the viewer that differences between the plotted lines come from changes in the model's parameters, not from changes in the input data. The code adds a legend to the plot, so viewers can clearly tell which line corresponds to each set of parameter settings. This legend labels the lines for the cheap and expensive configurations, making it easy to compare their results. By explicitly indicating which line represents which billing model, the legend greatly improves the clarity and usefulness of the plot. Finally, the plot is displayed using the show function from the plotting library, which renders the visual comparison of the billing outputs. This lets learners clearly see how changing different parameter settings alters the model's predictions. They can observe these differences even though the input sizes are kept the same, highlighting the impact of the parameters on the results. This script uses a simple linear billing model to show how changing parameters affects monthly energy bills for different home sizes. It defines two sets of parameters, one representing cheaper energy costs and one representing more expensive costs, then computes bills across a range of home sizes for both cases. It also prints a direct comparison for one specific home size to highlight the difference in bills. Finally, it visualizes the two sets of results, making it clear how the same home sizes can lead to different bills when only the model parameters change. Line examples. Picture a straight line that shows how study time affects exam scores. The horizontal axis represents study hours, which change from student to student and act as the inputs. The steepness of the line and the point where it crosses the vertical axis are parameters that describe how study time influences scores and what the score would be with no studying. These parameters stay fixed for all students and define which specific line we are using, while the different inputs simply move us to different points along that line. In this financial planning example, the number of months you save is the input, and it determines where you are on a line that represents your total savings over time. The fixed monthly deposit and the starting balance are parameters because they control the line's slope and position. When you change the input, you move along the same line, reflecting different saving durations. When you change a parameter, you switch to a different line, representing a different savings plan or assumption. Imagine a line that links how many minutes you walk each day to how many calories you burn. The walking time is the input because it changes from day to day and from person to person. The slope and intercept of the line are parameters that capture assumptions about your metabolism and how efficiently you exercise. If you keep these parameters fixed and change only the walking time, you move along the same line to get different calorie estimates. If you change the parameters themselves, you switch to a different line, representing new assumptions about your metabolism or fitness level. Python code. Line examples. This script is used to visualize straight lines by adjusting their inputs and parameters. It lets us compare different lines by changing those parameters and seeing how the lines shift. The main goal is to observe how input values move along a specific line as we vary these settings. By focusing on this movement, we can better understand the relationship between inputs and the line they define. This code relies on a plotting library called matplotlib, which is used to create visualizations. If matplotlib is not already installed, it needs to be added before running the script. Having this library available is important because the program will use it to draw graphs of data. These graphs let us compare different lines by changing parameters and seeing how different inputs affect the outputs. We begin by importing the plotting tools from the matplotlib library using its pyplot module. This gives us the ability to create two-dimensional plots that we will use to visualize our data and the lines produced in the script. With this module, we can generate and customize plots by setting labels, titles, and legends, and then display the final graphical output. We define a line model as a function that takes a list of input x values along with a slope and an intercept. For each x value, it multiplies the slope by that x, and then adds the intercept to get the corresponding y value. Doing this for all x values produces a new list of y values. This list represents the outputs of the linear function for the given inputs and parameters. This function returns a list of y values computed from the given slope and intercept. These values represent the outputs of the line model for the corresponding x inputs. With this list, you can visualize the line or further analyze how the inputs relate to the predicted outputs. We create a list of study hours that goes from 0 to 5, representing different amounts of time spent studying. These values serve as inputs to our line model, which predicts outcomes such as exam scores. By defining this range, we can calculate how the model responds to each study time and see how different parameter choices change the predicted results. We define a line that represents a gentle improvement in exam scores as study hours increase. Its slope is set to 5, meaning the score rises gradually as the input grows. The intercept is set to 40, so when study time is 0, the predicted score is 40. These two values together let us calculate predicted exam scores that reflect a slow, steady increase with more study hours. We now define a line that represents a stronger improvement. Its slope is set to 10, meaning the output increases by 10 units for every 1 unit increase in the input. The intercept is set to 40, which is the value of the line when the input is 0. Together, these choices create a line with a steeper upward trend, modeling a situation where improvements occur more quickly. To model a gentle improvement in scores, we use a line model that takes study hours as input and returns predicted scores. We set the slope to a small value and choose a matching intercept to represent slow progress. The model then calculates the corresponding score for each study hour, giving us a set of predicted scores based on these gentle improvement settings. We now calculate predicted scores for a case where improvement with study time is stronger. Using the same list of study hours, we apply the line modeling function again, but this time we choose a steeper slope while keeping the intercept unchanged. This produces a new set of predicted scores that increase more quickly as study hours go up. In other words, each additional hour of study now leads to a larger predicted gain in score than before. The code prints the list of study hours, which is the input data for the line models. Showing these values lets you verify that the correct data is being used in the calculations. This step helps ensure that any predictions made by the model are based on accurate inputs. It also makes it easier to see how different amounts of study time influence the predicted outcomes. We now print the predicted scores from the gentle improvement line that we calculated earlier using our line model. This output shows how the predicted scores change as study hours increase when we assume a slower rate of improvement. By examining these values, we can see the effect of using a smaller slope and a different intercept on the relationship between study time and expected performance. We now look at the predictions made by the line with the stronger improvement, meaning the steeper slope while keeping the same intercept. These results show the calculated scores for that steeper line. By examining them, we can see how changing the slope while leaving the intercept fixed affects the predicted outcomes. This helps us compare different parameter choices and understand their impact on the model's predictions. We begin by creating a new plotting figure in matplotlib, which sets up a fresh canvas for our visualizations. This canvas has a defined size, 6 by 4 inches, and provides the space where our lines and other elements will be drawn. Initializing a separate figure helps keep this plot organized and clearly separated from any other plots created in the same session. We use matplotlib to draw a gentle improvement line that shows how scores change with study hours. This line appears as blue circles connected by straight segments. The horizontal axis represents study hours, and the vertical axis shows the slow scores we calculated earlier. We call this the slow slope line, so it is clearly distinguished from any other lines in the plot. We plot the stronger improvement line by placing study hours on the horizontal axis and fast scores on the vertical axis. To make this line stand out, we draw it with red squares connected by lines. We also give it a label called the fast slope line, so it can be clearly identified in the legend of the plot. We use the xLabel function in matplotlib to set the label for the horizontal axis of a plot. In this example, we label it as study hours input X. This tells the viewer that the horizontal axis shows the number of study hours. Clear axis labels help people quickly understand what the input values on the plot represent. We label the vertical axis of the graph to show that it represents the predicted exam scores. This tells the viewer exactly what the Y values mean. Clear labeling makes the plot more informative and helps people interpret the results correctly. It ensures that anyone looking at the graph understands that the vertical position corresponds to the predicted score. The plot title highlights that the same input values, such as study hours, are used for all lines, but the resulting exam scores change because each line has different slopes and intercepts. This makes it clear that the visualization is about how altering these parameters affects the output. In other words, the title directs attention to the impact of changing line parameters while keeping the inputs constant. The code uses the legend feature from the plotting library to add a legend to the graph. This legend labels each line so you can see which line matches which set of parameters. It serves as a visual guide that makes it easier to compare and understand the different plotted lines based on their labels. The final line of the script calls the show function from the plotting library to display the graph. This step actually renders the visual representation of the data and the lines we created. It lets learners see both parameter sets plotted together on the same graph. In this way, it completes the plotting process and makes the underlying data and calculations easier to understand. This script shows how different linear models predict exam scores based on study hours. It plots two lines that start at the same initial score when study time is 0, but have different slopes, meaning different rates of improvement. The blue line has a gentle slope and represents moderate score increases as study hours grow, while the red line has a steeper slope and represents larger improvements. When you run the code, you see this comparison in the plot and also in the printed study hours and predicted scores, which highlight how changing the slope parameter affects the model's predictions. Understanding model equations. Reading prediction formulas. A prediction formula is a compact way to describe how different inputs combine to produce an output. For instance, predicting fuel cost for a trip uses inputs like distance and fuel price, with fixed numbers showing how strongly each one affects the total. Putting the formula into plain language reveals the model's assumptions, such as costs rising in direct proportion to distance, and the presence of a baseline cost, even if you travel no distance. By narrating formulas in everyday terms, you link the mathematical symbols to how the model behaves in the real world. To understand a prediction formula, first look at its overall structure to see whether it just adds inputs or combines them in a more complex way. Then focus on each term and ask what it represents in the real world. In a model for electricity usage, for example, different terms might stand for heating, cooling, or lighting, each multiplied by a factor that shows how strongly the model reacts to that input. If the factor for heating is larger than the one for lighting, it means changes in heating have a bigger effect on the predicted usage. Thinking this way helps you see how each part of the formula influences the final prediction. Once you understand prediction formulas, you can start to see how changing different inputs affects the output. For instance, in a model that predicts delivery time, increasing the shipping distance will usually increase the time, while making the warehouse more efficient will reduce it. The key is to focus on the direction and relative size of these effects, rather than exact numbers. By practicing with different scenarios, such as exam scores or sales forecasts, you develop an intuitive sense of how the structure of the formula and the values you plug in shape the model's predictions. Making sense of units. When using predictive formulas, it is important to check the units of each quantity so you understand what each parameter means and how it affects the result. Every term has units, such as dollars or hours, and these must be consistent. For example, if pay is calculated from hours worked, the parameter that multiplies hours should have units of dollars per hour, which tells you it is the hourly pay rate. Seeing how units combine helps you interpret each parameter and predict how changing it will change the output in practical terms. Unit analysis helps you see whether a parameter in a model changes the scale of an effect or shifts the baseline level. For example, in a model of household energy use, a parameter measured in kilowatt-hours per square meter shows how floor area affects energy consumption. So increasing it means larger homes use more energy. Another parameter measured simply in kilowatt-hours represents a fixed baseline usage that does not depend on area. By examining these units, you can tell whether adjusting a parameter will stretch or tilt the model's predictions, or move them up or down uniformly. By paying attention to units in a model, you can quickly spot unrealistic effects when parameters change. For example, in a health model, a parameter measured in calories per kilogram tells you how extra body mass affects calorie needs, and doubling it might give absurdly high calorie estimates for heavier people. A parameter measured in calories per hour of exercise instead controls how calorie needs respond to changes in activity. Interpreting parameters through their units helps you anticipate how adjustments will affect different scenarios, and check that the model's behavior is sensible before looking at exact numbers. Sanity-checking predictions. When using a simple predictive model, you should always pause and check whether its predictions make basic sense before trusting them. This kind of sanity check relies on common sense to see if changes in inputs lead to plausible changes in outputs. For example, if a model predicts rideshare costs from distance, raising the cost per kilometer should increase the total price, and lowering it should decrease the price. If the model behaves in the opposite way, there is likely a problem with how it was built or interpreted. The goal is not to get exact numbers, but to confirm that the model's overall behavior matches real-world logic. To quickly check whether a model makes sense, imagine pushing one of its parameters to an extreme and see if the output changes in a logical way. For example, in a project timeline model, greatly increasing productivity should make the project finish much sooner, while reducing productivity to almost nothing should make it take much longer. Similarly, in a sales model, doubling the impact of advertising should produce a much sharper rise in sales. If the model does not respond in these intuitive ways, its relationship between inputs and outputs may be flawed. Sanity checking means comparing a model's predictions to your own knowledge and to simple expectations. For example, if a model estimates daily calorie needs from body weight, then raising the calories per kilogram should lead to a reasonable increase in predicted calories, not an extreme or unrealistic value. If the model outputs something clearly off, such as an ordinary adult needing as many calories as a high-performance athlete, that signals a problem. The same idea applies in areas like finance or climate, where predictions should follow known patterns. Regularly asking whether the direction and size of predictions make sense helps keep models reliable and trustworthy. In this lecture, you learn to interpret simple linear equations used to express model predictions, differentiate between variables representing inputs and parameters representing model choices, and predict qualitatively how changing a parameter affects the output of a simple model. In the next lecture, Lecture B, we will go over probability intuition. Thank you for your attention. See you all in the next lecture.